Today we're on pages 276 and 277 of our textbook. You want to have a highlighter in your calculator. Lesson 5, Polynomial Identities. Recall that polynomials are expressions consisting of addition and subtraction of terms whose variables are raised to non-negative integer powers. Polynomials can have more than one variable. In other words, non-negative integer powers, it would be whole numbers. Exercise 1, which of the following is not a polynomial? Explain why. Powers here are fine. Choice 2 are fine. Negative 4 is not a non-negative integer, and 1/2 is not an integer. Polynomials can be rewritten using associative, commutative, and distributive properties. These rewrites can result in polynomial identities. What is a polynomial identity? First, an identity is an equation that is true for all values of the variable or variables. To prove an identity, rewrite one or both sides of the equation using algebra to make the two sides identical. One identity that we're already familiar with is x squared minus y squared equals x minus y times x plus y. This is the difference of perfect squares, factors into x minus y times x plus y. Test this identity using x equals 10 and y equals 3. Replacing x with, let me just rewrite the identity. So we're replacing x with 10. 10 squared minus and y with 3. 3 squared. Does that equal? I'm going to draw a vertical line segment underneath the equal, so I don't want to cross over the equal sign. Substituting 10 minus 3 and 10 plus 3. Okay, 10 squared is 100, minus 3 squared is 9, that is 91. 10 minus 3 is 7, times 13, 91. So it does check. The two sides are, we tested it, 91 does equal 91. Next it says to prove this identity by rewriting the right-hand side of the equation, making the sides identical. We want to rewrite the right-hand side. In other words, let's perform the operations here. You would draw that vertical bar in line with the equal sign. So we're using our double distribution. X times x is x squared. X times positive y is positive xy. Negative y times x is negative xy, and negative y times positive y is negative y squared. Combining like terms, the xy and the negative xy combine to be 0, so we have x squared minus y squared. The two sides are identical. Use this identity to evaluate the difference. 50 squared minus 49 squared. So 50 squared minus 49 squared would be equivalent to, so x is 50 and y is 49, so it would be 50 minus 49 times 50 plus 49. 50 minus 49 is 1, and 50 plus 49 is 99. It's equal to 99. And check on the calculator. 50 squared minus 49 squared is 99. Use this identity to simplify and then evaluate the product 51 times 49. Okay, so in this case, I suppose we want to rewrite 51 as 50 subtract 1 and 49 as 50 plus, I did that backwards. Write it as 50 plus 1, sorry, and 49 as 50 subtract 1. And that means that that would equal 50 squared minus 1 squared. 50 squared is 2,500, and 1 squared is 1. This result would be 2,499. And if I check using the calculator, 51 times 49, 2,499. Exercise 3, prove the identity. A plus b in parentheses squared equals a squared plus 2ab plus b squared. We are not going to use it to evaluate, so just cross that off. Okay, so a plus b squared equals a squared plus 2ab plus b squared. Draw a line, vertical line, in line with the equal sign. Now, there's really nothing to do here, but on this side, a plus b squared is the same as a plus b times a plus b. Perform this multiplication. In other words, a times a, and then a times b. B times a and b times b. B times a is ba, which is the same as ab. And b times b is b squared. Combining like terms, 1ab plus 1ab is 2ab. So we have a squared plus 2ab plus b squared, which does equal, it is identical to the other side. Sometimes identities have geometric connections. The Pythagorean theorem gives some identities. Exercise number 4, we have a right triangle is shown having sides 2x, x squared minus 1, and x squared plus 1. X squared plus 1 here is the side opposite the right angle. This is our hypotenuse. Show that these will be the side lengths of a right triangle when x is greater than 1. In other words, we want to prove that leg squared plus leg squared equals hypotenuse squared. 2x squared plus x squared minus 1 squared equals x squared plus 1 squared. Now, in doing so, I'm going to write this out to give myself some more room. So we have 2x squared plus x squared minus 1 squared equals x squared plus 1 squared. Well, it looks like we have a lot of squaring to do here. 2x squared, that's 2x times 2x, which is 4x squared. X squared minus 1 squared means x squared minus 1 times x squared minus 1. Doing the double distribution, x squared times x squared is x to the 4th. X squared times negative 1 is negative x squared. Negative 1 times x squared is negative x squared. And negative 1 times negative 1 is positive 1. Let's combine any like terms on this side. We have a 4x squared, a minus x squared, and minus x squared. Leaves us with a 2x squared. I want my exponents in descending order. I'll write the term x to the 4th first, and then plus 2x squared plus 1. On the other side, I could work on this side, squaring that. X squared plus 1 times x squared plus 1. Again, the double distribution, x squared times x squared is x to the 4th. X squared times 1, x squared, 1 times x squared, 1 times 1. Combining like terms here, we have x to the 4th plus 2x squared plus 1. The two sides are identical. So we prove this identity. Exercise number 5, prove the following identity by expanding both sides. Let me just go back up. If I wanted to just work on one side in exercise number 4, once I got to this point here, I could have factored, right? If I take this trinomial, the factors of positive 1 that sum to 2 are 1 and 1. So this would be equivalent to x plus 1 times x plus 1. But we have an x to the 4th, so it's really x squared plus 1 times x squared plus 1, which can be rewritten as parentheses x squared plus 1 squared, in which case the left-hand side would be identical to the original right-hand side. And going back to number 5, prove the following identity by expanding both sides. A squared plus b squared squared. That means a squared plus b squared times a squared plus b squared. Double distribution. A to the 4th plus a squared b squared b squared times a squared is a squared b squared times b squared, b to the 4th. Combining like terms, a to the 4th plus 2a squared b squared plus b to the 4th. Now on the other side, a squared minus b squared times a squared minus b squared plus 2ab times 2ab. Double distribution. a to the fourth minus a squared b squared minus a squared b squared plus b to the fourth. Two ab times 2ab is 4a squared b squared. Combining like terms, so we have a negative, these combine to be a negative 2a squared b squared, and a positive 4a squared b squared is a positive 2a squared b squared. Write a to the fourth plus 2a squared b squared plus b to the fourth. They are identical. Exercise 6, consider the polynomial identity. A plus b cubed is equal to a cubed plus 3a squared b plus 3ab squared plus b cubed. Prove the identity by expanding the left-hand side of the equation. Hopefully I left myself enough room. A plus b raised to the power of 3 is a plus b times a plus b times a plus b. Okay, so multiplying the first pair of binomials, double distribution, a squared plus ab plus b squared. Combining like terms here, we have a squared plus 2ab plus b squared. Bring down, put that in parentheses, wrap it in parentheses, bring down the third binomial. Now I'm going to distribute, let's see, I'll go with a squared times the a plus b. We get a to the third plus a squared b. 2ab times a plus b. Plus 2a squared b, and 2ab times b is 2ab squared. And b squared times a plus b, ab squared plus b cubed. Combining like terms, we have a to the power of 3 plus 3a squared b plus 3ab squared plus b cubed, which equals the other side. And we are not using our calculator, we are not doing b. So we are done. And once again, I thank you very much for your attention.